Hello, Accelerated Chemistry students. This is Mr. Spurk, and this is your Chapter 18, Section 1 notes on the rates of reaction. A rate is a measure of how much something changes within a specified amount of time. In chemistry, the rate of a chemical reaction, or the reaction rate, is usually expressed as the change in the amount of reactant or product per unit time. A model called collision theory is used to relate the properties of particles to the rates of chemical reactions. According to collision theory, atoms, ions, and molecules can react to form products when they collide if the particles have enough kinetic energy. Particles that do not have enough energy to react bounce apart unchanged when they collide. So we can look at an effective collision would be one that involves oxygen molecules and hydrogen molecules colliding and producing H2O, which is what we have below. So that would be an example of an effective collision. And an ineffective collision would produce no reaction. So it would just be these molecules bouncing into each other or colliding and not in the proper formation, so it wouldn't work and we would have no reaction. The minimum energy that colliding particles must have in order to react is called the activation energy. You can think of the activation energy for a reaction as a barrier that reactants must cross before products can form. When two reactant particles collide, they form what's called an activated complex. An activated complex is an unstable arrangement of atoms that forms for a moment at the peak of the activation energy barrier. And this activated complex lasts for like nanoseconds. It occurs, it reaches that maximum energy, which we call that activation energy, and then we go back to our products. The lifetime of an activated complex is typically about 10 to the negative 13 seconds. So it's actually like picoseconds. Its a brief existence ends with the reformation of the reactants or with the formation of products. Thus, the activated complex is sometimes called the transition state. The activation energy barrier must be crossed before reactants are converted to products. So if we look at this graph here on the right, you see there's the energy of reactants on the left side, and you can see those particles colliding and they reach that peak activation energy. That's our activated complex or our transition state. And then we have them falling back down to a lower energy. That would be the energy of the products. So that activation energy is the difference between the peak and the energy of the reactants, because it's the energy that the reactants must overcome. And the energy from that second spacing for the energy from the energy of the reactants down to the energy of the products, that's the energy that is released by the reaction. So here we're looking at an energy diagram for an exothermic reaction. Remember, an endothermic reaction absorbs heat. An exothermic reaction releases heat. So here we're going to look at, this is an endothermic reaction because the energy of the products is higher than the energy of the reactants. So you can see that the reactants need to reach a much higher energy for this reaction to occur. Collision theory explains why some reactions are extremely slow at room temperature. Carbon and oxygen react when charcoal burns, but the reaction has a high activation energy. The O to O bond and the C to C bonds must be broken to form the activated complex. At room temperature, the collisions of oxygen and carbon molecules are not energetic enough to break the bonds. Thus, the reaction of carbon with oxygen at room temperature is essentially zero. So they don't have enough energy when they collide to form that activated complex and form the products at room temperature. So there are factors that affect reaction rates. Temperature is one of them. Usually raising the temperature speeds up the reaction because it increases the frequency of collisions. Concentration is also a factor. The number of particles in a given volume affects the rate at which a reaction occurs, because that also increases the collisions. Think about being in a room full of people. The more people that are in that space, the more frequently you're going to bounce into them. Particle size is also a factor. The total surface area of a solid or a liquid reactant affects the rate of reaction. The smaller the particle, the greater the surface area is for a given mass. Another way to increase the surface area of a solid is to dissolve them. You can also increase the surface area of a solid by grinding them up into a fine powder. A catalyst is another factor, and a catalyst is a substance that increases the rate of reaction without being used up during the reaction. And catalysts permit reactions to proceed along a lower energy path. So catalysts they don't actually participate in the chemical reaction, but they do affect the rate. So the activation energy barrier for the catalyzed reaction, or when a catalyst is used, is lower than that of an uncatalyzed reaction. When that barrier is lower, a greater fraction of the reactants have the energy to form products within a given time. So if you look at the dark purple plot, that one it has a lot larger of an activation energy, and that's the one without the catalyst. But if you look at the light purple diagram, or pink maybe, you can see that the activation energy is a lot lower, and that's because we're using a catalyst. So this reaction is a lot easier to occur with a catalyst because the activation energy is a lot lower. So we can look at this reaction here. This reaction does not occur at room temperature unless we have that platinum catalyst being used. So we can't just collide H2 and O2 molecules to form water, but when we use a platinum catalyst, this reaction can occur at room temperature. The catalyst, platinum, is not actually consumed during the reaction. It's just there, it helps it happen faster, and then it's still there at the end of the reaction. An inhibitor is a substance that interferes with the action of a catalyst. Reactions slow or even stop when a catalyst is poisoned by an inhibitor. So an inhibitor kind of sounds just like what it would do. It inhibits the reaction from occurring, or it inhibits the catalyst or slows it down. All right, so that's it. In review, in chemistry, the rate of a chemical reaction, or reaction rate, is usually expressed as the change in the amount of reactant or product per unit time. Factors that can affect the rate of a chemical reaction are temperature, concentration, particle size, and the use of a catalyst. All right, that's it for section 1. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry, 2012 edition of the textbook, the resources CD, and pearsonchemistry.com. Have a great day, guys.